Hello all, this is Dr. A. Anuja, Assistant Professor of Department of Mathematics, Arulmigu Palani Andavar Arts College for Women, Palani. In this lecture, we are going to discuss about Varigon's theorem of moments. So the statement of theorem, the algebraic sum of the momentums of two forces about any point in their plane is equal to the momentum of their resultant about that point. So we have to prove this theorem in two cases. In case 1, we consider the two parallel forces. So those names are P and Q. These two parallel forces which are acting over any point in their plane. Now we draw AOB, which is perpendicular to the forces to meet their line of actions in A and B. So the resultant of P and Q is force, and R is equal to P plus Q, because sum of the two forces is equal to R. Its R is nothing but the resultant of the two forces which is acting at C, such that P dot AC is equal to Q dot CB. It's nothing but which is get it from definitions of the momentum. It's the definitions of momentum is the momentum of force about a point is defined to be the product of the force and the perpendicular distance of the point from the line of actions of the force. From this definitions, we can write P dot AC is equal to Q dot CB. And P is a force, the AC is a perpendicular distance for the force P, and CB is perpendicular distance for the force Q. And in the figure, we'll take the parallel forces P and Q, and they'll give a resultant force R is equal to P plus Q. So therefore the algebraic sum of the momentum of P and Q about O is equal to P dot OA plus Q dot OB. Here OA we can written as OC minus AC, and OB we can written as OC plus CB. We'll get the result is equal to P of OC minus AC plus Q of OC plus CB. And then next we multiple with P to the terms, and we multiple with Q to OC and CB. We'll get equal to P dot OC minus P dot AC plus Q dot OC plus Q dot CB. Here P dot AC is equal to Q dot CB. So we are replacing for this and take OC as a common. We'll get OC of P plus Q, plus we replacing P dot AC as in Q dot CB. So we are cancelling these two and we'll get OC into P plus Q. P plus Q is nothing but the resultant force, that is R is equal to P plus Q. So for this P plus Q is an R. Finally we'll get R dot OC. So it's nothing but momentum of R about O. And the figure B, O is within AB, and the algebraic sum of the momentum of P and Q about O. So we can write P dot OA minus Q dot OB. We can written as OA as OC plus CA minus Q into CB minus CO. So we are multiple with P to the terms and Q multiple with CP and CO. So we'll get P dot OC plus P dot CA minus Q dot CB plus Q dot CO. Here we are replacing P dot AC as in Q dot CB. So we'll get OC of P plus Q plus Q dot CB minus Q dot CB. So we are cancelling these two and we'll get OC of P plus Q, and P plus Q is nothing but R. So we'll get R dot OC. It's nothing but momentum of R about O. So here when the parallel forces P and Q are unlike and unequal, the theorem can be proved exactly in the same way. Next, the case 2. Here we are assuming the forces meet at the point at A. Let the forces P and Q are which is shown in the figure 1 and 2, and next we let QO be at any point in the airplane. So through the figure 1, draw the line parallel to the directions which meeting the line of actions of Q at D. So choose the scale of this represent the length AD represent Q in a magnitude. So on the same scale, the length AD represent Q in a magnitude. On the same scale, the length AB represent the point B. So we are completing the diagram. We'll get a parallelogram. It's named as PAD. So the diagonal AC represent the resultant R of the forces P and Q. In either figure, the momentum of P, Q, or about O are represented by 2 triangle AOB, 2 triangle AOD, and 2 triangle AOC. which are respectively. And in figure 1, the O is lies outside the angle BAD. In figure 2, the O is lies inside the angle BAD. So for we have to find these two cases about O. We'll find the momentum of forces P and Q. The first one, O is lies outside the angle BAD. The momentum of P and Q are both positive, and the algebraic sum of the momentum of P and Q equal to twice the triangular of AOB plus twice the triangular of AOD. So we here the triangle AOB equal to triangle ACB. We are replacing triangle AOB as a triangle ACB, and also the diagonal AC bisects the parallelogram. So we are replacing AOB, triangle AOB as triangle ADC. So the final result 2 is equal to ADC plus the triangle AOD. We are taking 2 as a common, and we are adding to these triangles, will get a triangle AOC, and twice the triangle AOC, it's a momentum of R about O. And the figure 2, in the figure O is lies inside the angle. So the momentum of P and O here, it's a positive while the Q is negative. So the algebraic sum of the momentum of P and Q will get 2 triangle AOB minus 2 triangle AOD. In same way, previous case we proved, in the same way we proved this, will get a 2 triangle AOC. It's a momentum of R about O. So therefore, in theorem, the algebraic sum of the momentum of two forces about any point in the plane is equal to the momentum of their resultant about that point. So hence proved. Thank you.